Jain to all. Today I'm here to present the second video lecture of the series Control System BEC 602, and the topic that I have chosen is Signal Flow Graph. I am Dr. Amit Garg, Associate Professor in Akgec Garg Engineering College. So let us see Signal Flow Graph. So the diagrammatic or pictorial representation of a set of simultaneous linear algebraic equation of a more complicated system is known as signal flow graph. So earlier we have gone through the concept of block diagram reduction. So in case of block diagram reduction, we are having a complicated system. That system is represented through the blocks. But here in the case of signal flow graph, that block is replaced by these simple lines or branches, you can say, and the gain of each and every block is written over it as a transmittance. And so with the help of algebraic equations, we can make a signal flow graph and also find out the overall transfer function of the system. Signal flow graph applies to linear systems. So it is important to note that signal flow graph can only be applied to the systems which are linear in nature. It shows the flow of signals in the system. It is important to note that the flow of the signals in SFG is only one direction. Okay, so whenever we will talk about the signal flow, signal will only be in one direction. To represent the set of algebra using SFG, it is necessary to that those algebraic equations are to represented in S domain. Okay. The transfer function which is represented by SFG can be obtained by using Mason's gain formula. So there is a method which is given by Mason's gain formula, in which we can easily find out the overall transfer function of the given function based on the number of forward paths, based on the number of loops, self loops, and all that. Based on that, we can find out the overall transfer function of the given system, and that approach is basically given by Mason's. So that's why this is called as Mason's gain formula. The dependent and the independent variable in the set of algebraic equations are represented by nodes in the SFG. Like you can see in case of block diagram, we are having two type of things, like one is takeoff point, another one is summing point. So here all those takeoff point and summing points will be taken as the simple nodes. Okay, and in between nodes branches are present, and at each and every branch transmittance of that corresponding branch is written. And so the branches are used to connect different nodes present in SFG. The connection between the different nodes is based on the relationship given the algebraic equation. Okay. So now we will see the various terminologies that can be used in case of signal flow graph. So first one is input node, or you can also call it source node. So basically an input node is a node that has only outgoing branches. Okay, it means if we are having a signal flow graph, this is your signal flow graph, you can say, and here is node 1, 2, 3. So you can say this node 1 node is basically the input node, and output node is node that has only incoming branches. Okay, so let us suppose another node is A and you are having transmittance like this. So you can say this node 4 is basically the output node. So third one is a path. Path is any collection of a continuous succession of branches traversed in the same direction. The definition of a path is entirely general, since it does not prevent any node from being traversed more than one. So we can see all those things. So according to this is the input node that we have already discussed, and this is the output node, and we are talking about the path. So path is any, like this, you can say this is a path, and if you can see this is a path, and if you can see this one is a path. Okay, and another thing is forward path. So forward path is a path which basically connect from input node to output node. Okay, so a forward path is a path that starts at an input node and ends at an output node, and along with no node is traversed more than one. So it is very important to note down that we cannot traverse through a node again and again. Okay, means if you will take this path like G1, G2, G3, G4, G5, G6, G7. So this is your forward path. But if we are taking G1, G2, G3, G4, G5, G10, G6, G7, so this will not be a forward path, because this node is traversing twice. This node is traversing twice. So we cannot take it as a forward path. And then path gain. The product of the branch gains encountered in traversing a path is called the path gain. So let us suppose we are taking this particular path. This is also a forward path, and the gain of this forward path is nothing but G1, G2, G3, G4, G5, G6, G7. Okay. And then forward path gain, then loop. A loop is a path that originates and terminates on the same node and along which no other node is encountered more than once. Like here you can see loop. You can see this is basically a loop. This is basically a loop. This is basically a loop. Okay. This is basically a loop. Okay. This is a loop. Okay. Then loop gain. The loop gain is the path gain of a loop. So like if we are moving in this path, so this transmittance is G3, this is minus H2. So the path gain of this loop is minus G3 H2 simply. Non-touching loops, two parts of an SFG are non-touching if they do not share a common node. So you can see here, like this is basically a loop, and this is also a loop. But you can see in this is loop 1, this is loop 2, let's say. So this is the common node in between. So you can say these two nodes are touching with each other. So you cannot say these are two non-touching loops. But you can see if you will see this path and if you will see this loop, so you can see there is no common node in between. So that these 2 and 3 loops are basically non-touching in nature. Okay. Or you can say this is, let's say, fourth loop. So you can see each and every node 1, 2, each and every loop 1, 2 and 3 is non-touching with loop 4. Okay. And self loop, the path that starts from one node and ends at the same node without traversing any other nodes in a self loop. The self loop is also a type of closed path since the path starts and ends at the same node. Okay. So you can see this is your self loop. This is your self loop. You can easily see that starting and end point is the same. So it will make a closed loop. Okay. So here are the so these are the concept of basically non-touching loops, forward path gain, self loop, input node and output node. Okay. So now we will see this Mason's gain formula. What this Mason's gain formula said. So you can see this is the overall transmittance or overall transfer function of a system, where we can see the formula is Pk delta k upon delta. So the terms in the Mason's gain formula can be explained like Pk is the forward path transmittance of kth path from a specific input to an output node. Means first of all we have to find out how many forward paths are present in a given signal flow graph. Okay. So let's say if it is 3, then k value equals to 3. In asserting Pk, no node should be encountered more than one. So again it is the same thing like when we are finding P1, P2, P3. So all should be, you can say you cannot, you can say that it should not be the same. Means we are not encountering more than once. Okay. And delta is basically the graph determinant which involves closed loop transmittance and mutual interaction between non-touching loops. The formula that we can calculate for delta is 1 minus sum of all individual loop transmittances plus sum of loop transmittance product of all possible pairs of non-touching loops minus sum of loop transmittances product of all triplets of non-touching loop. Means we will find that how many loops are single loops, how many loops are non-touching loops, how many pairs of 2 non-touching loops, how many pairs of 3 non-touching loops, and like that. So accordingly we can find out the value of delta as per the given signal flow graph. Delta k is basically the path factor. So delta k is the path factor, means if there are 3 paths, let's say P1, P2, P3. So according to each and every path P1, P2 and P3, there will be 3 delta k, that will be delta 1, delta 2 and delta 3. And delta 1, delta 2 and delta 3 simply can be calculated like delta 1 is equal to 1 minus, we will subtract here the loop transmittance which is basically you can say which is touching the forward path 1. So which is touching the forward path 1, we will minus the transmittance of that particular path. Okay. And with the concerned path involves all closed loop in the graph which are isolated from the forward path under consideration. The path factor delta k for kth path is equal to the value of the graph determinant of signal flow graph which exists after erasing the kth part from the graph. Okay. Now let us see some problems now this is the first problem. You can see a signal flow graph is directly given to us. So we can solve it. Another thing is that it is also possible that there is no signal flow graph given, but block diagram is given to you, and it is written that you have to find out using Mason's gain formula. So what you have to do? First of all, in that case, you have to convert block diagram into signal flow graph. So simple method for doing this is that your takeoff points and summing points of a block diagram will be replaced by nodes here, and the blocks which are connecting in between will be represented by single branches, and each and every branch is having some transmittance value which is written over it. Okay, so you can see like here G1, G2, G3, G4, all are the branch transmittances. Okay, so now if you see this problem, so in this problem we are having 1, 2, 3, and 4, 5, and 6 nodes are there. Okay, 6 nodes, and now we have to check that how many forward paths are there. Okay, so here we can see the first forward path that we can take as 1, G1, G2, G3, G4. You can see this, and it is connecting N1, N2, N3, N5, and N6. So, and this is the first forward path, and the gain corresponding to it is G1, G2, G3, G4. Next forward path that we can take is basically you can see here G1, G5, and G8 and G4. So you can see this is the second forward path, which is going from N1, N2, N4, N5, and N6, and the branch transmittances are G1, G5, and G8, G4. Okay, so the path gain is G1, G4, G5, G8. Okay, then third forward path, you can see there is no other forward path present here in the signal flow graph. Only 2 paths are present because you can move only in this direction, and later you can move only in this direction. Okay, so there is no other forward path exists. So this is P1 and P2, which is the forward path gain of 2 paths. Then the number of individual loops present in this SFG. So individual loops, you can see that one loop is this G1, G2, H1, another loop is G3, G4, and you can see so transmittance corresponding to G1, G2, H1, and for this G3, G4. Then another loop is basically you can see, and this G5, G6, G5, G6. This is also a loop, individual loop. So this is G5, G6, and another loop is, you can see this. This is not a symbol. This is a self loop. So we will consider it also. So this is basically the self loop. Okay, and another loop is you can see here. You are moving in this direction. So this is another loop. Okay, so this loop is G1, G5, G8, G4, H1. Okay, so this is the transmittance. So all these are individual loops. Okay, so if we will sum it all, then it is G1, G2, H1 plus G1, G4 plus G5, G6 plus G1, G4, G5, G8, H1 plus G7. Now we will see the product of gains of combination of 2 non-touching loops. Okay, so 2 non-touching loops, if you will see here, we are having 1, 2, 3, 4, and 5 loops, 5 individual loops. Okay, so now we can see that if you will see the gains also, again you can identify it. So like first one is G1, G2, H1, and G4, G7, means this one and this one. You can see these are 2 non-touching loops. So L1, L3 will become or L2 you can say G1, G2, G7, H1. Another one is we are taking this with this combination. Okay, so you are having this transmittance. Then uh, and you will take this with this also. Okay, so there is another combination like this. So these are three pairs of two non-touching loops, and you have written the basically the transmittance corresponding to it, and then so you are writing this as S2, and now we will see if there exists okay. So this is basically now we will see what is the determinant of delta 1, delta 2 and all that. So delta 1 is delta 1, if you will see, delta 1 is corresponding to path P1. So you will check which loop is not touching with this forward path 1. So you can see this loop, this loop, this loop, this loop, all are connecting except this which is self loop. Okay. So that's why this N4 means we will reduce it 1 minus, you can see transmittance is G1, and delta 1 and delta 2, if you will see, delta 2 is your forward path 2, you can see this forward path is touching with all the loops, so delta 2 will become 1, so delta 2 is 1. Now you can write the formula simply P1 delta 1 plus P2 delta 2 upon delta, where delta is 1 minus sum of all individual loops. You can see this is S1, and later on this is S2, and here you can see this is P1 delta 1, so P1 is this, and P2 delta 2. Delta 2 is sorry, delta 1 is you can say 1 minus G7. So you will multiply it, so you will get this term, and this term is corresponding to P2 delta 2. You can see the value of P2 is given here, G1, G4, G5, G8. Okay, so this is how we can apply the Mason's-Gain formula to solve the overall transfer function of a given signal flow graph or a given system easily. Now obtain SFG system whose block diagram is given below, and obtain the transfer of given system using Mason-Gain formula. As I have already told you, in this type of situation, first of all, we have to convert this block diagram into the signal flow graph. So here you can see one node is corresponding to this, another node is corresponding to this, and another node is corresponding to this, then another node is corresponding to this, then another node is corresponding to this. It is important to note, like here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is important to note whenever some takeoff point comes just before summing point, then we will take those two nodes as separate nodes. Okay, and whenever takeoff point comes just after summing point, and then we will take those as a single node. Okay. So we have converted this like in this case, and the feedback, like here you can see this H1 is connected with negative feedback. So what we will do in case of signal flow graph, we will write it minus H1. Okay, so similarly this is minus H2, and you can see this. Okay, so now in this particular question you can see that how many forward paths are present. So one forward path is G1, G2. Another forward path is G1, G3, and there is no another forward path. So you can see this P1 equals to G1, G2, P2 equals to G1, G3. Now if you will talk about individual loops, so individual loops are like minus G1, G2, H1, and minus G2, H2, and G1, G3 minus G1, G3 minus H2, G2 minus H1. Yani it means G1, G2, G3, H1, H2. Now you can see if we'll talk about these loops. So all these three loops are touching with all the forward paths. So it means the value of delta 1 and delta 2 will become 1. Now delta, there is no pair of non-touching loops. All loops are touching with each other. So only individual loops are there. So delta will 1 minus sum of all individual loops. So we'll write it like, and this is the value of delta. And C by R, or the overall transfer function, can be written like P1 delta 1 plus P2 delta 2. So it means G1, G2 plus G3 upon 1 minus sum of individual loops, which we have already calculated the value of delta over here. So this is the answer. Okay. Now another problem where a block diagram is given to us. So again we will check, this is one node, this is second node, this is third node. Okay, and it is your fourth, fifth, sixth. Okay. So when we will draw the signal flow graph, corresponding signal flow graph can be written like this. So in this case, if you will see, there are how many forward paths and how many loops or how many non-touching loops, if you will see. So you can say there are 6 forward paths. One is ABD, one is ABD, another one is EFH. The direction is there, direction is this. Like, okay, ABD, EFH, and AJH, similarly EID, and then minus EI minus CJH, and similarly minus AJGID, minus AJGID. So these are the 6 forward paths. And if we will talk about the individual loops, then individual loops are minus BC, minus FG, and another loop is which is not seeing so easily is like this. This is also a loop because at this point there is no connection. Okay, so you can see the transmittance of third loop is ICJG, and all the loops are touching the forward path. You can see P3, P4, P5 and P6. But what about P1 and P2? So correspondingly delta 3, delta 4, delta 5 and delta 6 is 1, and delta 1, you can see delta 1 path is not touching this loop FG. Okay, so this will become 1 minus of FG, so it will become 1 plus FG. And delta 2 is basically similarly forward path 2 will not touch this loop, minus BC transmittance. So it is 1 plus BC. And now we will see the 2 non-touching loops. So these 2 loops are non-touching with each other. It means BCGF. If we will solve it, it will become BCFG. L1 into L2 is BCFG. So delta is 1 minus sum of all individual loops plus multiplication of loop transmittances. So we are having this value of delta. Okay. So this is how we have calculated all these like forward path, individual loops, path factors, non-touching loop graph determinant. And if you want to write C by R or overall transfer function, so it will become nothing but P1 delta 1 plus P2 delta 2 plus P3 delta 3 plus P4 delta 4 plus P5 delta 5 plus P6 delta 6 upon delta. By this you can easily find out the value of overall transfer function. This is another question. Here we have to find out, here given it is y7 by y1 of the given size using measure, also find y7 by y2. Okay, so y7 by y1 is simple because this is output node and this is the input node. Okay, so if you will solve it, there are 2 forward paths, G1, G2, G3, 4, and another one is G1, G5, and this delta 1 is 1. Okay, and because all the loops are touching with forward path 1, but for forward path 2, G3H2 is a loop. This loop is not touching forward path 2. So this is 1 plus G3H2. So, and there are 4 loops, minus G1H1, minus G3H2, and one is minus G2N, G2, G3H3, and minus H4. This is the self loop. And pair of 2 non-touching loops, it means L1, L2 are non-touching, L1, L3 are non-touching, L2, L3 are not touching, and L3, L4 are not touching. And if we'll talk about pair of 3 non-touching loops, there is also existence of pair of 3 non-touching loops, which is L1, L2 and L4. So this is minus G1, G3, H1, H2, H4. Okay. So delta we can write it like this. So y7 upon y1 is simple. G1, G2, G3, P1 delta 1 plus P2 delta 2 upon delta. Now to find y7 upon y2, first we need to find y2 upon y1. So it is important to note that for finding y2 upon y1, the value of delta remains the same. So we will not change the value of delta. So if we'll see between forward path y1 and y2, we will see there is only a forward path y1 and y2 is p1, which is equal to 1, and delta 1 equals to, we will see all the loops which are not touching with this forward path from here to here. So this is 1 minus L1 plus L2 plus L2 plus L4. Okay. So you will find that delta 1 equals to 1 plus G3H2 plus H4 plus G3H2H4. Now y7 upon y2, if you have to find, you can write it like y7 upon y1 upon y2 upon y1. So y2 upon y1, you can see whenever you have to find out y7 upon y2, because you will see that delta will be in the new denominator and it will be vanished like this. So there is no need to calculate the value of delta. Okay. So you can put the value over here, and y7 upon y1 and y2 upon y1. Okay. So y2 upon y1 is this upon p1 delta 1 upon delta. So this is delta. So it will cut down. So y7 upon y2 can be find like this. Okay. And so when it is happened, then you have to check that delta 1 will become 1 minus sum of all individual loops. Okay. So all the loops will be considered which are not touching this. So that's why we are obtaining this. So this is how we can calculate the value of y7 upon y2. Okay. And these are the references for which I have used for this presentation. Thank you. Thank you so much.